Delighted to announce to invite sorry to point out that my colleague Devika Subramanian will give me a talk today. I've known her since we were both grad students way back when in the 1980s. We've done some collaborations. We did a whole workshop on the relevance of relevance from way back.
Oh my gosh.
An AI Journal article. She's given many invited presentations in 2 invited talks at ICHKI on different topics. At the Office of Naval Research, I was UW, an invited speaker at the Grace Hooper Conference, as well as a Heart Failure Society of America. She's been program co-chair for III and on many advisory boards, has received many teaching awards at Stanford, Cornell, and Rice. So she's done a lot of fun things, a lot of very interesting topics. I'm looking forward to her talk, and hopefully this will be the start, at least of many collaborations with me and many colleagues. Devika, all yours.
Thank you, Russ. It's such a pleasure. And thank you for that very generous introduction. I'm truly looking forward to interacting with you all. So today my talk is titled Big Data and Machine Learning, Challenges and Opportunities. I actually struggled to come up with something that would be interesting. And I have to say I began life as an engineer. I came out of the IITs. In India, and then went to Stanford and worked on AI and machine learning and the relevance. My thesis was on irrelevance. The big idea was, well, what if machines could design their own representations and we're all set to go, right? And we can work on things we want and machines will take care of the rest of the universe. So alas, I think we're still on that project. We haven't quite solved it. But that was a theoretical piece of work. Then my first academic job was actually at Cornell, which is sort of the bastion of all theory. But that was where I found a new religion, and that is, let's do things that other people care about, which is the engineering philosophy that I was trained on as an undergraduate. Since then, I was there at Cornell briefly and then moved to Texas, Rice University. And I have been, my motto in picking problems is the following. First of all, is the problem interesting to me? And does anyone else other than me care? And if the answer to both those questions is yes, then I jump in, head first. So, and you will see the results of 4 of those topics. I'll also give you a brief review of things I'm currently working on. I'll mention that I am looking for postdocs to come join me in the problems I'm working on. So I hope I can excite some of you in here. So here's my perspective. This is not novel. I mean, a lot of us have the same thought. How do we exploit the massive amounts of data we gather to help answer questions that matter to us? It's a very broad kind of range of broad question. But I see that the role of AI and machine learning is really enabling us to use all this information, sort of make objective decisions rather than sort of assuming the lotus position and intuiting the answers. So if we can actually have data support or evidence support our conclusions, that would be good, I think, for everyone. So I've been doing this for a long time, and a lot of good people have invested in me. So everything that I'm going to talk about is really thanks to all of these lovely people. So let me just give you a sort of an overall sort of view of how I view machine learning / AI and even artificial intelligence. So I think almost all problems, at least the ones I'm going to be showing you today, kind of fit within this framework. There is a complex system that we don't fully understand. This could be the T-cell signaling network. If it's, it could be, your buying preferences, your behaviors. I mean, Amazon has a model just like this, except a complex system in this diagram is you. You can't look into the complex system. It's a black box as drawn. But what you can observe are the inputs and the outputs to that system. And that forms our training data. Armed with enough training data where you observe the system over some period of time, and armed with prior knowledge, because knowledge is always a good thing, can't learn everything from data alone. We build learning algorithms, the little green box here, which is where I spent most of my work, to design predictive models, and that's the focus of today's talk, where the goal is to come up with actions to control this complex system to achieve our objectives. So if you're Amazon, the complex system is you, the action is to get you to buy stuff so they can make more money. The training data they have is all kinds of minute data about how you navigate their website. Prior knowledge is actually knowledge from other people who also shop on that same interface and who they can cluster and sort of map to people who look like you, or who, by look, I mean who buy like you. And then they build a predictive model and they show exactly the things that you want to buy. So I have to say, today, Amazon actually knows me better than my husband of 33 years. It knows exactly what I want for my birthday, mostly because now we buy everything off of Amazon. So it has a pretty good model of me. So that's the idea. We observe a complex system and we build models to predict its response, and then we use that response to achieve some kind of objective. So that's the role of the big data, because we're going to really rely on observations coupled with perhaps more observations or other general purpose knowledge in order to build predictive models. So the fundamental questions that arise, they're common across all the problems I'm going to talk about today. What data should be gathered to make predictions? So this is an important problem. It's a problem that occupied me as a PhD student. To solve a particular problem, what aspects, what should I really represent for the machine? This goes by the name of data selection, feature selection, still an unsolved problem. And I will give you through the examples, the 4 examples I have for you, kind of how we solve this. What class of models to build from observed data and prior knowledge? This is the model selection problem. What is the form of this model, the mathematical structure of this model that will enable us to actually make predictions about the behavior of the system? And then finally, once you have the data, you have selected the model, you also want to put together or put in place a system for validating the model. How do you know you've got a good model? This is the model validation problem, and obviously we have a few methods in our field to come up with ways of understanding whether you're generally doing well or not in the predictive context. And finally, what algorithms should we use to learn these models from data? So once you have your data, you have selected your model family, you've selected a protocol for validating your model, then comes the actual computer science work of figuring out exactly what algorithm to use to learn that model, and how to actually integrate the learning algorithm within the flow, the decision-making flow of this complex system. So those are hard problems, and particularly in the clinical world, that can prove to be particularly challenging. And I'll touch upon it in the context of building a model for predicting esophageal cancer in the early stages. So these are old problems, okay, well known. The hope is to sort of push everything forward by really trying to understand, by working on a whole range of problems and then trying to abstract from them exactly what makes, how to approach these problems even in the first place. So most learning algorithms, as you all know, is essentially an optimization problem. How do you select the most likely model given the data? So you have a space of models, you have data to constrain your, to help you select which among these models are great. And your learning algorithm is essentially some kind of optimizer, some kind of either greedy or stochastic gradient descent or some kind of optimization family. Well, I wish I could say that what I will show in the next several minutes is theoretical answers to all these questions, okay? The reason I'm not doing that is because I don't have such an answer. Okay, so the cartoon here says, the beauty of this is that it's only of theoretical importance and there's no way it could be of any practical use whatsoever. Not the approach I have. I'll tell you what I have followed in my, for the last 20 years or so. I design and validate algorithms for real world, socially relevant problems, or so I like to think, and I'll give you some examples. I publish in the application community journal and get them to use the methods. Then I come back to my own community after I do abstract task level analysis and present it to the machine learning people. So in the course of doing this, what I have understood is sort of, how to develop representations, how to formulate problems. So what is rarely emphasized in machine learning and often relegated as second-class activity is applying a method to a problem. And I'd like to, if the one message you leave with at the end of my presentation is, application is not a second-level activity good for people who just don't have the ability to do something else. It actually is a very creative task. And if you want to build good solutions, you really have to have good ways of handling, modeling. So I'm a problem solver at heart. Never met a problem I didn't really like. So, which is probably why I have adopted this kind of approach where I seek the problems and work with domain scientists to understand the problem. And in the course, I've gotten inspired to come up with new algorithms and new approaches. So I've been doing this for a while. So many of my projects are in medicine and clinical data analytics because I'm just across the street from the largest medical center in the United States. And this is the Texas Medical Center. So I've worked with the Baylor College of Medicine, UT Health, as well as MD Anderson, and done a whole bunch of work with them. I will touch upon, today I'll be talking about predicting esophageal cancer from NBI images. This is a project I had with a team at the University of Nottingham who were kind enough to give me data and work with me and allow me to shadow them to understand how they did their work. Lots of projects in social sciences and social media analytics. Today, I will talk about understanding attitudes to gun control in America from Twitter data. We're also doing a similar project with anti-vaxxers, which is sort of highly relevant in today's climate. Finally, lots of projects in engineering, natural sciences, and computer science. My current projects are in weather forecasting and learning chaotic dynamical systems, predicting wind and flood damage risk, which I will talk about today, as well as predicting human behavior from data, from neuroscience data. So this is in the context of a training task. I worked on it with the Navy for that piece. So, in case I lose you in the details of these problems, I want to sort of summarize my talk right now. So if you want a quick post-lunch nap, you may do so. But here's what I have found or what I have learned. The most difficult part of machine learning is determining what is worth predicting and from what information. While we have a plethora of algorithms that will take, matrices X and predict Y, continuous or discrete, oftentimes when you're armed with such an algorithm and you go to say, all right, I'm going to help you predict which of these type 1 diabetic kids are going to develop a diabetic ketoacidosis. It's not even clear. Is that problem solvable? Do we have tools for saying which problems are actually predictable? Do we have the right information to predict it from? All this is still very empirical. So I spend most of my time determining what is the relevant set of information from which we can predict what we want to predict, what is worth predicting. In a lot of cases, we actually don't have gobs of data, particularly in clinical medicine. It's very hard unless you are Google and you just purchased Kaiser Permanente, very hard to get huge data sets. So I'm currently working with Texas Children's Hospital. They're the largest pediatric hospital in Texas and 3 or 4 surrounding states. And yet I'm lucky for a 10-year period, I have about 2,500 type 1 diabetic patients, pediatric patients. So really ensembling has become a key tool for building models. And that actually allows us to combat data heterogeneity. When you perform predictions under uncertainty, it's worthwhile to gather information over time rather than gathering it one shot. Both in the study of chaotic dynamical systems as well as in the clinical course prediction of disease, gathering predictions over time, information over time, rather than a one-shot, get 50 measurements at this time point. If you have a budget of 50, spread it out over a period of time and take 6 at 8 points in time, turns out to be a much better investment of your data resources. Network analysis techniques reveal temporal dynamics in data. There are some interesting open problems here, and I hope to interest you in them, because I think when you look at the evolution of Twitter graphs, tweet, retweet graphs, I think there's a lot of opportunity for interesting mathematics to understand how they sort of grow and shrink. And finally, and this it will be made clear in the final project I'll talk about, integrating multiple sources of information at varying spatial and temporal scales is key to making robust predictions. So I built a system for my city of Houston, where people could get an estimate of their damage to their homes at the individual home level, with oncoming hurricanes. So you have risk from wind, you have risk from flooding due to rain, risk of flooding due to storm surge, and also risk of power loss. We built a model that's able to give at a very individualized level, very granular level, predict sort of what is the risk so people can make decisions about whether or not to evacuate. Probably not a problem in Edmonton because you're not on the coast, but we routinely get bombarded by hurricanes. And I have been subject to the ill effects of at least 2 in the 20 years I've been here. So this is a problem that's very close to my heart. Well, when you go talk to people who want to use machine learning, and right now it's practically the whole universe, they all think, okay, here's the data, all right? Come back in 2 months and tell me, give me the model. And it takes me a long time to persuade them that that's not how it works. And the reason we haven't gotten all this automated, even though we have hyperparameter tuners and a whole lot of other algorithm selection tools and so forth, is that the real problem is this is a process where you have to go back, get more data, and so forth. In fact, one of my meetings earlier today was negotiating with the Texas Children's people. We're developing models for being able to diagnose a very bad complication of COVID in children. It's called multi-inflammatory syndrome complex, MISC, and we want to be able to diagnose it right with a very small panel of tests and to do it right when they are in the ER or in an outpatient clinic. So, so I was begging them to give me more data because my analysis reveals I need more cytokines to tell me what the situation is. So this is a back and forth. It's not just a straight through loop. But most of you probably already know that, so I won't dwell on that point. So in what follows, I am just going to run through 4 of the problems I've worked on and highlight the questions I asked earlier, those 4 questions in terms of defining a machine learning project and how we answered them. So here's the first problem. This is the problem of detecting esophageal cancer at an early stage. Now, the good thing about, well, esophageal cancer is a deadly cancer, often diagnosed in the late stages, and therefore nothing much can be done. So, but if you detect it early, there's a very good chance that it can be, well, I wouldn't say cured, but certainly managed. So there is a new sort of imaging technology called narrowband imaging with magnification, which allows you to look at the detail of the surface, the mucosal morphology and microvasculature in the endothelial, that's the outermost layer, cell layer in the esophagus. So those images, I'm going to show you examples of those images in a moment. But here is the problem. Very experienced doctors can detect lesions in these images, cancerous lesions in the very early stages with 75% probability. But the residents and people who haven't had much experience, they do as well as a coin. So the problem is, can we do better if we built a predictive model directly from the labeled data? So the data is labeled with biopsies, so we know for a fact whether there is or isn't a cancerous lesion in that system. This is a hard problem, by the way. If it were easy, the doctors would have figured it out. One of the difficult problems is that there is no vocabulary to describe the surface patterns in the epithelium and the vasculature. It's not a quantitative vocabulary. And we humans need those in order to communicate our understanding to our students. So that's why there's considerable human judgment and subjectivity involved in interpreting these images. The NBI images were given to 4 different centers, 2 in the UK, 2 in the US, and then they did, they combined the judgments and tried to determine how well people were doing. And basically this statistic that I quoted, 75% in experienced doctors and 51% in the less experienced, is derived from that multi-center trial. So clearly there is need for perhaps automated assistance in terms of interpreting these images. here's the data that I got. There's a paucity of data because it was at the time a new imaging modality. I got 210 images, 45 with biopsy-confirmed cancerous lesions. And these were all from Barrett's patients. So Barrett's is a precursor to esophageal cancer. So what happens in Barrett's is that, if you have reflux, the cells at the bottom of your esophagus, the esophagus is a tube connecting, the gullet all the way down to the tummy. And basically the endothelial layer becomes like the stomach. And that's not good because the esophagus has to have, has a certain other function, and those cells get replaced by stomach cells, which is not good. So that condition is called Barrett's. And then once you are diagnosed with Barrett's, you will be subject to a 3-month follow-up where they will do endoscopy, upper level endoscopy, and collect images to make sure there are no lesions that are potentially cancerous. So this was the first set I got. A year later, they sent me a whole load of new images, 75 images. So I actually got a nice test and train configuration just by the accident of how I got the data. So what you're seeing here are, these are all non-cancerous lesions, but this sort of begins, and I've shrunk the images. These are very detailed. These are large images. You can see all the specularities. You can see the variations depending on whether you got an end-on view of these little tubules, or that's an end-on view where you see little, see that over there, like skin. They're really end-on views of these spaghetti-like structures. Predictive accuracy of expert doctors can be anywhere from 50 to 75. These are the good ones. These are the Barrett's cases. And these are the very obviously bad cancerous lesions. You can see that with the level of blood in them, the irregularity in the vasculature, the irregularity in the structures of the endothelial cells. So the point is, okay, you're given these two classes of images. Now can you, and it's not too many. So, so your answer can't be, oh, let's do deep learning and you're done, right? So you can't, there's just not enough data to build a deep learning model. So the doctors really wanted a model, and they wanted it to be built into the tip of their tool so that they can, regions could be highlighted, the potentially lesion containing regions. So here's what I did. I said, all right, it drew upon the course I took with Tom Binford as a graduate student. I took my vision class, and I said, all right, we'll actually use all the computer vision that I know, and we'll learn in order to solve this problem. So I ended up actually taking the raw image, separating out the channels because blood is better visible in the green channel, and did some segmentation, intensity normalization, and then merged the objects from all of the 3 channels to build a composite map where I identify the objects in the image as I have shown, and calculated all kinds of statistics about these images, about those objects that I segmented out. So these are the kinds of features I extracted. These kind of structures that you see are called pits. So I counted up how many pits are there. What is the density of the pits? Given a pit, how many surround it? How many non-pit-like objects are there? Like how many total objects? How many of them are pits? Pits are these little tiny things that you see. What's the average intensity of each of these objects? A whole bunch of things, some based on color, like mean pit hue, and some based on shape, irregularity, so how elongated it is, and also intensity. So there are 11 features, okay? So this took me a while to develop, I'll have you know. And so this was the final protocol. Training images, yeah, Barrett's images. I had the high grade lesions, early cancer, did the feature extraction using that pipeline that I just showed you, 11 numeric features, ran a random forest ensemble classifier. Then I got those 75 new images, and it did a pretty good job. So this was nice. The doctors were thrilled, I'll have you know. And while these were not possibly, I left out a whole bit of the story where I spent 3 months shadowing these doctors trying to understand, what should I focus on? I have no idea. Tried to talk to the doctors to understand, what should I look at? Why did you call this containing a lesion? Why? And finally I said, talking to them is pointless, right? They gave me classification schemes that they had developed, and I implemented them. I spent a lot of time, a year, just that's all I did, day and other than day and night, other than of course my teaching duties. So this was a hard one. But of course, doctors being who they are, they said, yeah, that's essentially what we're assessing. Well, great, excellent. But now we're working to actually work with the Olympus company to build this classifier in, so that when the tool goes in, we'll build it at the tooltip in FPGA, so we can actually get these rectangles while we're doing this. So this is work in progress, but at least we know the method works, and those features are very, very stable, because it was tested on a whole different set that I never had access to when I was doing the training. Along, similar kind of idea, but what's different here is that here I had only one modality of data. Okay, I only had the image data. Right now I'm working on a problem, and we're finishing up the paper to go into diabetes care. This is the Diabetes Journal, working with 2 diabetes people in Texas Children's Hospital, where we look at lab data, procedures data, health history data, demographic data, in order to predict which among the type 1 diabetic pediatric patients will go on to develop a really bad complication of type 1 diabetes called diabetic ketoacidosis. So we can actually predict from a small set of measurements what the, with 0.8 accuracy, we don't have a crystal ball. I'd love to say it's a crystal ball, it isn't. But it's better than, only the chief of endocrinology has performance as good as this. So if we can have every resident perform at this level with the help of our tool, we're trying to build it into the clinical flow right now. So yeah, so lots of opportunities, particularly in clinical medicine. If you live across the street from Texas Medical Center, and they are really now more than ever, this is thanks to the resurgence of AI and the perception in the public, they want to incorporate these tools into their regular clinical flow, and they're willing to work with us and actually ask tough questions about, how do I know your model's any good? So interpretability of models, I've really had to push upon that, because my the people who validate these models, remember I said validation is going to be very important. The people questioning the results of my models are the doctors, who have a pretty good idea about how this disease works. So very few things surprise them. But actually, one of the things that did surprise them was the fact that these 4 markers out here that they collect routinely when they diagnose someone with type 1 diabetes turn out to be rather important in predicting the course of the disease. That was a revelation, and that will actually be the focus of the paper that we're working on right now. Okay. Lots of other clinical problems, and I would love to talk to you at the end about other opportunities and what the challenges are in working with them, working with this kind of data and modeling. Surprisingly, it's not the big data problem there. It's the fact that you have very little data, and you really have to bring in a lot of medical knowledge and build that into your models and constrain them, so you don't build models that violate sort of the physics of the human body. So there's a lot of opportunity to build those kinds of models. So let me see if this is going to work. So I'll segue as quickly as I can into this other problem that I worked on many years ago, but which is still my favorite project. So I thought I'd share this with you, because I don't know how many of you have seen this work. So, the Navy, the ONR actually got in touch with me. At that time, I was working on reinforcement learning, and they had a game that they would have all their submarine commanders, people in submarine school, play. So let's see if this actually works. Oh, thank God. So anyway, this is just a progression of a game. So you're piloting a submarine through mine-infested waters, and these are the 3 sensors that you've got. One is a sonar sensor that gives you sort of sonar readings with a 140 degree forward field of view. So the cone of every one of these is 20 degrees, and there are 7 of them. So this is dead ahead, and then this goes like 20 degree segments, just 140 degrees forward. You have to make a rendezvous point, and this tells you how far you have to go. And there's also a timer. So you need to get to the rendezvous point before time runs out. The sonars are noisy. So, and the red circles that you saw when you're playing the game, that tells you when it's very big, it means there's a mine very close to you. If you touch a mine when you are navigating your submarine, you blow up. So this is a very stressful game, by the way, and you have 30 seconds to play it. So in real time. If you want to understand how it feels, imagine you're dropped into a very strange room with a lot of chairs and tables and other obstacles. There's exactly one exit out of that room. You don't know where it is. You have a talking compass that tells you the overall direction to that door that you need to get out of. There's a loud ticking clock going tick-tock, tick-tock, telling you time's running out. And then you have a noisy sonar that kind of tells you in which general direction the obstacles are lie, but that too only in a 140-degree forward field of view. So you have to turn if you want to get information from other parts. It's, trust me, not a pleasant game. I could never win the game. My only revenge was I could write programs that could learn to play the game, but I myself could never do that. At the time, my daughter was 8 years old and could play this with ease. So apparently 50% of the people training to be in submarine school can't play the game. So the Navy was interested in a couple of questions. Is this the right game to be testing for future submarine commanders? It was designed by some admiral in the Navy and was supposed to kind of select people who, I suppose, have what it takes to succeed in the submarining or commanding a submarine. But really, what makes this game hard? That was one of the questions. And why do 50% get weeded out? Like, what's going on? Is this something to do with the game, something to do with humans? Like, what's going on? So this is the actual setup of the game that we never reveal to our subjects. Okay, so what the game that you saw a moment ago, this is sort of what the subject did. Okay, and now I can watch it because I'm the, so you can see. If I showed you this map, it's trivial, right? You'd do it. But what's difficult is, of course, that these mines are very close to one another. You have to get awfully close to the mines if you want to get to the rendezvous point before time runs out. Okay, so you have to have a certain level of risk-taking ability. Many of our subjects would basically get to the edge of the minefield over here and dither because there are mines everywhere. Now what do you do? So, oh, sorry. So these are some learning curves. We did hundreds of these experiments and they get very cluttered, but more or less all the equivalence classes are represented here. On the x-axis, we have the number of games that you play. So the way the Navy runs this game is you get to play 500 games, 100 per day. At the end of that 500 games, you're given 10 games. If you get 8 out of 10, you're in, otherwise you're out. Okay, that's the protocol. We ran our subjects a little longer, gave them,
Clarification question. Every game is different, or is it the same mind?
Every game is different. Oh, I forgot to tell you.
Thank you.
This is just a random layout. So you cannot memorize 3 lefts, 4 rights, and whatever, and play this game, okay? You actually have to have, so that's why I said mind configuration changes with every game. The game has a strategic and a visual motor component, okay? So you have to have a plan in the sense that in this configuration, I should do this, and this other configuration, I ought to do that. Now, I believe for myself as a player, I think I know what to do in each of these circumstances. What I don't have is my visual motor component integrated with my strategic component in my head. And so there's an impedance mismatch between my brain and my visual motor loops. I can never execute the wonderful plans my brain makes. Okay, so I can never play this game. So you will see that a lot of people just never improve with time because this is the success rate. There are others who improve, and you can see the improvement goes in plateau, then goes up and plateau, and they never recover. Then there are people like this yellow person who keeps going up. And basically, this one has reached the limit of what we've seen a human do. All right. So unsuccessful learners are basically dead on arrival. It doesn't matter how much experience you give them. But successful learners look awfully similar. You know, they have plateaus, and then it's like they go up, and then there's something very interesting going on. And what machine learning was able to tell us was what exactly is going on. Why do these characteristic curves appear? I've already spoken about this. Why is the game hard? What's the source of complexity? Why have we never seen a human do better than 80%? Why do some humans learn and why do others fail? Can we detect inability to learn early enough to intervene? That is basically, can we shape human learning on the task? So this is what we did. Well, actually, we did a lot of things that didn't work. So I'm only going to tell you the things that did. So initially, we actually talked to the people who failed and said, what were you doing? Like, what was your strategy? And then my graduate students and I would implement all those strategies laboriously. And what we found is the strategy they said they were doing and then the actual strategies viewed for the gameplay had nothing to do with one another. So we said, we're not going to talk to these people anymore. We are going to instrument the joystick, and we're going to tie the, we're going to look at what they're looking at with eye trackers, and we're going to instrument the joystick so we can actually get a coordinated data set of what they're seeing and what they're doing. So we have this time series of they saw this, they did this, they saw this, they did this, right? A whole mapping like that. And what we did was we inferred their strategy from these very low level data. Okay? We were able to not only extract the strategy, we were able to study its evolution over time, and that helped us understand the learning profiles. Of course, there are a lot of challenges, right? The data, the visual data we're getting, it's in 11 dimensions. They're all discrete, actually, as it turns out. So it's a total size of 10 to the 14. So we're mapping a 10 to the 14 sensor space to a, an action space, which is this discretized space that I have shown. So the joystick is also discrete. And so you have, 1, 2, 3, 4, 5 choices of turns and 10 choices of, 5 speeds and 10 turns, something like that. So 50 choices. So it's a mapping from some 10 to the 14 object to a 50 object of size 50, very large volumes of data, noise in data, and it's non-stationary because people's policies change over time. This is how a person behaves. Subject 1, day 2, the most important action is 0, 0. They're doing nothing. They're just standing there. But you can see that as they learn, you can see that action, the frequency of that action comes down, and now they're turning. You see that the turn actions are coming, which is good. That's what they need to do. So this is what we did. We built a mapping from the sensors to the action distributions over a window of games. And we represented that as actually a raw table from these configurations to this. No abstractions. So you might say, well, that sounds stupid. Didn't you tell me there are 10 to the power 14 sensor configurations and you're going to maintain maps of that size? Well, here was the amazing thing we discovered. Only 1,000 to 10,000 of them were actually observed when over a training run of 600 episodes. So not all 10 to the 14 sensor configurations actually occur during gameplay. So this is why this object is actually very, very tractable. So we're exploiting sparsity in the sensor configuration space to build what we call a direct model of the subject. And the direct model takes the raw sensor and maps it to the distribution, the two-dimensional distribution over the space of actions. So how do strategies evolve over time? We take one window of episodes where we have mappings from the sensor configuration to the action distribution for that sensor config. Then we have another one over a certain window. And we basically compute the KL divergence between those two mappings. All right, that's it. And here's what we see. So along the x-axis, again, we have the episodes. The red graph is actually the learning curve, which sort of on a moving window says how many episodes have they won. And the blue curve is the what I call the policy derivative curve, or this distance function between strategies. So take a window of W, slide it over, and then do another W. and then calculate the KL divergence between those two windows. You will notice it has a very characteristic structure. So it starts high, then settles down, starts high. So when you have a low value of KL divergence across two successive windows, that means there's not a whole lot of change in the action distributions corresponding to particular sets of configurations. But you notice these peaks, right? So these are where radical changes in policy are occurring. And we are measuring it directly from the sensor data. So we're no longer talking to the people. So what we find is there is, for all successful learners, there is this period, and even these peaks, where they adopt a strategy, refine it incrementally, abandon it, refine it, abandon it, pick up a new one, refine it, and so forth. So you see this kind of characteristic peak valley pattern followed by mostly refinement, while you let the policy soak into your visual motor loop. So learning continues to improve because you're training your visual motor system. You have discovered a good policy for playing this game. All right. So all successful people look like this. And even the inter-peak spacing is very characteristic. So that seems to be like a human thing about how long should you hold on to a strategy before you abandon it. So take a look at this particular peak. We have 2 games before and after that. So this happens within a space of 20 games. So it's very fast. Here's a person playing tentatively, and they will run out of time. But 20 episodes later, oh, I'm sorry, maybe I didn't shift this. Right, episode 320, you can see that they're much more confident. Their action distribution has shifted. They're able to make the goal. So you might think, well, those people who fail, what do they look like? So all successful people look alike, but people who fail, like Tolstoy said, right, they're all have their own stories, but they're broadly 2 equivalence classes of failures. This is the more interesting class of failure. The most common form of failure is inability to shift strategies at all. So they will have a single peak, and then there'll be refinements. They just don't understand the feedback they're getting from the game, which is, this is not working is what the game is telling you, but they don't have the capacity to come up with something new. But here's a very interesting form of failure, and that is, notice the spacing of the peaks, right? They're coming really fast. They don't give it time to work through the visual motor loop. So the result is, so this is a very creative person, but hasn't understood that the brain and this visual motor system have to be coordinated if you really want to succeed on this game. So these people, we pulled out of the protocol and actually have to slow them down so that they can succeed in playing this game. So now we understand the shape of the characteristic learning curves. Subjects have relatively static periods of policy choice, punctuated by radical shifts. And successful learners have conceptual shifts during the first part of training, and unsuccessful ones either keep trying till the end of the protocol or just give up at some point in time. And now you can tell this before the 5 days are up, because by looking at these strategy derivative plots, you can tell whether this person's really going to make it or not. So the Navy was super thrilled with this. So we went ahead and showed them these models are really good, because what we did was we trained a model by observing a subject for 4 days, 400 games. And then we had the model, so we learned the model, and we had the model play and the subject play on the 5th day. All right, so let's see how that works. In fact, we went a little crazy, and we actually confirmed, these strategy peaks. We confirmed in EEG data. We found that these strategy peaks, before they appear in the visual motor data, they appear in the neurological data at a particular time constant apart. So if we plot the neurological strategy derivative, you would see it just prior to when it appears in the visual motor data. So we have confirmed that, and this is the setup. This is how we collected all the data, by the way. So To generate those behaviorally equivalent models that I talked about, we built a very, very simple model to compute the action. So the model was just to look up. It's essentially a locally weighted regression model. We did an LWR looking up for the 4 days. We just store all the sensor configurations and chosen action distributions in a particular way, and take 100 neighbors, and they're temporally all sorted. So you take the most recent ones that they did, so you have the most recent distributions. And then we'll look at the actual subject playing this and then the model playing the game. They're the same games. You'll see that they play quite equivalently, but not identical. And we did this for 100 games, by the way, but oh, sorry, I didn't shift this. Something doesn't work here. Okay, now this is day 2, sorry, the day 5, second episode. Oh. No, I should also show you this, shouldn't I? In fact, the fit between the model that we acquired out of the 4-day training and the actual subject, oh, here we go. This is the actual subject's learning curve on that last day. We ran them for 150 episodes for this bunch of, and our LWR technique did extremely well fitting the subject's performance. So we can model subjects on this task in real time, achieving excellent fits to their learning curves using the available visual motor data stream by actually cutting out sort of the, so we no longer talk to them or try to infer what they're doing. We infer it directly from the low-level data. And I believe this is one of the first attempts in cognitive science to directly use objective visual motor data to derive evolution of strategy on a complicated task. We also can predict performance on that task on new examples, as I just demonstrated at the very end. Of course, at this point, you're asking, all right, where's the science, right? So you've turned lead into gold, good. Do it again, write a detailed description, and submit it for peer review. Well, we did all that. And we got a number of things published. And you can look at my Google page to get all these papers. But the lessons I learned from this project was that simple models learned from objective low-level data outperform any kind of abstraction that we may have built or inferred from subjects. Non-stationarity is our enemy here because things are changing. So you have to design learning algorithms that are robust to it, detect change points in the time series, and be able to shift. And that's what that strategy derivative allows us to pinpoint where that action distribution has a major shift. And so we ended up developing fast new algorithms for detecting change points and building predictive stochastic models for these, high-dimensional, noisy, non-stationary vector time series data. So that was our intellectual contribution, though we certainly had fun building these videos, showing matches with actual subject data. Okay, I'll pause a minute. I won't spend too much time on this before I run out of time. I'll just have time to talk about this project and not the one that is closest to my heart, which is predicting wind risk models for Houston. So the question I started with was, can we accurately infer public opinion on political or social issues by monitoring Twitter? So I have to say, since I come from India, where guns are highly regulated, nobody has guns. Only the police have guns, I guess, and only some police have guns, not even all. I don't know what the gun laws are in Canada, but I'm assuming they're very sensible. But in the US, everyone, including, the guy sort of monitoring activity in the supermarket has a gun, which sort of really concerned me. But anyway, that's a topic of some interest to me. So I wanted to find out who are the major voices in this debate on gun control. How come the US has been unable to pass a reasonable gun control law? And with the rise of all these social media platforms, including Twitter, we need to see exactly what does the public feel about it. Lots of challenges trying to answer these questions from Twitter because you have 140 or 280 characters. You can't do big time NLP analysis, very non-stationary time series. But what we found complicating our analysis was the presence of significant number of bots, and they basically dominate the conversation. So why do we focus on Twitter bots? So if I want to understand the question of interest, which is what does the American public feel about gun control, if we had to control for the bots. Why is that? 2016, we certainly saw this phenomenon, lots of tweets, well, for Trump, and with shortened URLs like this, all right? So if you clicked on those URLs, okay, another one like that. If you clicked on them, like that one, basically it would lead you to malware. So a lot of people were writing the Trump thing, you know, to get their message heard, you know, whether they were selling you fake Gucci watches or trying to install antiviruses on your machines. So we did a study on the prevalence of bots, like how prevalent are these? So 9 to 15% of Twitter accounts are bots. This was a measurement from 2017. And 50% of tweet traffic is generated by bots. That number has more or less remained steady. Well, we all know bots are bad. I don't have to belabor that point. What we developed was a brand new way to detect bots. So the standard approach to detecting bots, pioneered by a group in Indiana, is to actually collect bots, you know, hand label them, collect features, you know, describing those accounts, and then you have a classifier, and then you run it on all the extant accounts on Twitter and try to identify them with a bot or not score. So the system is called bot or not. They keep changing their name. It used to be called bot or not. You type in the Twitter handle into that website, and it'll give you a probability between 0 and 1 of it being a bot. So unfortunately, though, even it's not very good, because almost everything works out to be about 0.5. So if you typed in Obama's name, it would say 0.47 is a bot. So that's not a good sign. So, and that's a problem with the supervised approach, because this is a moving target, right? Once you know, once the baddies figure out how you're detecting them, they go and change, somewhat like the spam problem. So what we did was an unsupervised approach. We don't need label data. We basically detected groups of accounts tweeting similar texts over a period of time, and which tweet shortened URLs like the kind I showed you. So like here, these kinds of things. See, here are 2 separate tweets, different accounts, and they more or less have the same text. So why focus on shortened URLs? Because if you look at the traffic on Twitter, real-time trending URLs on Twitter, you will actually find that a lot of the shortened URL services, which are the red things, Bitly, DBLR, YouTube, Owly, etc., Google, these are the ones that actually, most of the URLs are actually from URL shortening services. You might wonder what du3a.org is. That's actually a service for tweeting Quran prayers in your name. So rather than actually say the prayers yourself, you can subscribe to a service that will tweet the prayers on your behalf. So that's one of the most widely used services. I won't go into the details of how it's a complicated process. We crawl the Twitter, then we detect these duplicates as approximate duplicates. We group them according to the URLs, the shortened URLs they're tweeting, by following where the URL leads us to. And then we form families of these accounts. And then we're able to detect these groups of Twitter bots. There are, and we actually got them from various sources, and you can find there are certain URL shortening services where most of the accounts, you know, we were able to detect 894 bots out of the total number of accounts that tweeted these shortened URLs. You know, fortunately, Twitter was able to catch about 50% of them. But then there are these Bitly bots. Twitter only, you know, suspended 8.9% of them. So there is differential enforcement of bots. So we actually contacted Twitter, and I'll have a few words to say about that in a moment. Oh yeah, we got a lot of mention. This paper of ours got covered on media, including Vice. We also discovered exactly how the whole process works. We reverse engineered the process by which people were using Twitter as a platform. So the idea was first to set up these malicious websites. This could be malware, the fake Gucci watches, or all these junky sites we'd never go to. You register that, and then you create bots. And for all of these, you use these URL shortening services to direct traffic here. You make a tweet with a trending news item cut and pasted from Reuters or BBC, and at the end you put a little URL. So you might actually put in a trending news item here, and then a link created this way. So you trap a lot of people into coming and clicking in your site. This is exactly how they work. So we were able to sort of reverse engineer and figure out who these baddies were. And then we told Twitter about it. So Twitter actually changed their policy. And now they are catching people using our method, which is they do not allow users to simultaneously post identical or substantially similar content to multiple accounts. And we gave a tech talk there at the end of 2017. And by 2018, February, they rolled out a new policy, which is gratifying. They actually found use for detecting bad people on Twitter. So I'm already at 2 o'clock. This is awful because I was going to show you the evolution of opinion on Twitter. So, I'll spend a minute and just show you. This is the Parkland shooting, 2018, a mass shooting at Stoneman Douglas High School. And we followed Twitter traffic on this shooting for 5 weeks, from March 1st to the 5th of April. And I want to show you the dynamics of how there are 2 groups in the country, the anti-gun group and then the pro-gun group. And we'll show you how they evolve over time, which sort of points to the real problem we have with passing gun control here. So right after the shooting, this is 2 weeks after the shooting, the biggest cloud, these are all, so we did a whole bunch of analysis here, which I won't be able to go into. We built tweet, retweet graphs. These are huge data sets, millions upon millions of tweets. So this large group that we've got here are the people who are fighting for gun control. They're mostly people who are affected by the shooting, like Cameron Kasky, a student, Shannon Watts, a mother who lost her son, and so on. If you look at the details of this, they're all the people who are directly affected. And here are the usual suspects. Chris Cox, NRA, he's the president of the NRA, the Fox News host Tucker Carlson, and all these real James Woods, real MAGA Steve. So you'll see the MAGA theme coming up over and over. This is a very small group. This is the big group, all right? So this is what happens, right? The anti-gun group is almost 80% of the traffic. The pro-gun group is 20%. And the people who are spearheading it are student, mother, TV host, and paper of record. NRA president, actor who's a conservative Republican, Fox News host, and this is a bot. Then 1 week later, same deal. This is still, the green group is looking strong. CNN and NBC have jumped into the anti-gun group. Emma Gonzalez, student at the school. Kyra Perro, same. Pro-gun are all the, Fox News, NRA TV. Kyle Cashew, who's unfortunately a student at the school who is for guns. His admission to Harvard got rescinded. And Dana Lish, I think a Fox News person. All right. Still, you can see things are looking good. But the anti-gun group is growing. This is a very big, this is a bot. We discovered this is a bot. The others are what we saw the previous week. Then Rand Paul came in, and now you can see, senator who's a libertarian, and you can see this group seems to be shrinking. Not a good sign. The major media have left. ABC News is the only one standing at this point. The mother, Shannon Watts, and the robot, the Twitter bot, educating liberals, Rand Paul, NRA TV as usual. You can see the pro-gun is growing. This is 29th of March. Again, we're analyzing this, and what we find is the program group still growing bot, 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 bot. And now the only person in the news talking about it is good old John Oliver. Everybody else has tiptoed out of it. The NBC, the ABC, CNN, they've all moved on to the next story. And then final, the last week we took, this group has grown very, very strong. The loudest voice in this group is a bot. We thought this was a bot, but this turns out to be an actual woman named Candace Owens. You can see all these are the usual suspects, the NRA, Fox News, etc. And here you can see the mother and a few other people. Cynthia Nixon was running for governor of New York at the point, and she still has a thing here. But what's really interesting is we recolored that network by showing you the bots in red. Do you see that the tweet network shows that the entire conversation arguing for guns and against gun control is really kept afloat by all these red spots. These are the bots in the conversation. This also has a few bots, but not nearly enough. So now we know kind of what we're up against and what the social media systems will have to do to counter these voices so we can see the true representation of people who are for sensible gun control versus not. So bots amplify polarized online political discussions, particularly on the right. The news media participation, the attention span is very low, which is bad. If you don't control for bots, it superficially looks like the American public is divided 50-50. That is not the case after you control for bots. But definitive identification of bots is still a problem because bots are always, you're playing a, they're always changing their strategies. So I don't know how many more of the accounts that we see here are actually bots. These are the ones we could detect using our techniques. I'll stop here. I've already indulged, taken up a lot of your time, but I wanted to show you what kinds of analyses we can do, with machine learning and data. So I'll stop here, take questions, and if there's interest in these, I can show you select things.
Wow, thank you very much. That was marvelous. I could spend another hour listening to the wonderful things you're talking about. People have to leave, of course, should head off.
I understand. Sorry about that. I timed this to be 1 hour. I don't know. Maybe I'm speaking at thrice my normal speed. So
maybe it's a Canadian time zone. It's all this.
No.
Other questions here? So some of your first topics, yeah. Okay, so I guess there's some questions right now about visualize the Twitter network. So the tools you developed for finding bots, is that publicly available? Can we?
Yes. They are publicly available, and I can point you to, there's a GitHub, and I can point people to that. Or I'll send it to you. I'll send you the link to the GitHub. You can take a look at, and also the papers. They should be available from my Google Scholar page. So don't look at I'm still updating my my homepage. So go to my Google Scholar page that has all of my current all of my current stuff. So
we'll have to have you come out again and talk about this model.
This is a great model. But some of the new things I'm working on are on pharmacovigilance. That's this paper. You can see that on my Google Scholar page, and then predicting population stratification effects for predicting mortality, hospitalization rates for SARS-CoV-2. More pharmacovigilance stuff, and then some work I've been doing on building predictions for chaotic dynamical systems using machine learning. This is where we did the this is the paper that showed that echo state networks, which are these recurrent networks, were basically reducible to L1 regularized logistic regression. So very proud of that little piece of work. So if you follow that, it's available from my Google Scholar page. Go check it out.
Okay. I have about 5 or 6 questions, but I probably should just arrange a separate meeting with you because lots of stuff I want to talk about, some of the work I'm doing that relates to this. But
great, Russ, we can find time next week and do that. It doesn't have to be done this moment. So and it's probably a longer conversation. I'd hate to rush anyone at this point.
So let me ask other people to if questions.
Chime in, yeah. Maybe I can also see the chat. Let me see. Yeah, chat.
There's been a few questions.
Oh, what did you use to visualize the Twitter network? Okay, it is a software. It's a very clunky. Okay, it takes a lot of patience to use. It's a package called Gephi, Gephi.
Okay. I'm going to head off. So Sabina, are we still recording? Yeah.
Yep,
Okay.
still have it going.
Thank you very much. We'll talk to you later.
Thanks, Russ. And yeah, we'll set up. Yeah, I understand. People have to go. I apologize for running over. Somehow, this was all going to go so fast. And I would have had like half hour to talk. And I would take questions, that is. So.
Thanks very much, Devika. And I'll touch base with you.
Yeah.
Send you
If there are any other questions from people, I can hang around for another couple minutes. So, yeah.
I'll stop the recording now. But
Yeah,
again, if anyone wants to stay, feel free. I'll leave the meeting running.
Thank you. Thank you, Sabina. Appreciate it.
Devika?
Yes.
Can you hear me?